Let's begin with a strange fact about modern CPUs. Your processor regularly executes instructions that might never actually happen. It performs calculations based on guesses about the future. Sometimes those guesses are correct. Sometimes they are completely wrong. And when they're wrong, the CPU simply throws the work away and pretends it never happened. This technique is called speculative execution, and it is one of the most important performance mechanisms inside modern processors. Without speculation, today's CPUs would be dramatically slower. In this video, we're going to explore
why CPUs need speculator.
What exactly the processor is guessing about, how speculation works inside an out-of-order pipeline, how wrong guesses are detected and recovered from, and why speculative execution changed both performance and security in modern computing. To understand speculative execution, we first need to understand a problem that appears in every CPU pipeline. The problem, waiting kills performance. Imagine a CPU pipeline executing instructions. A modern processor might have a pipeline with 15, 20, or even 30 stages. Instructions are continuously moving through this pipeline. Fetch, decode, rename, dispatch, execute, write back, retire. Each stage is designed so that one instruction can move forward every cycle. In theory, this allows extremely high throughput. But in practice, instructions often cannot proceed immediately.
Sometimes they depend on data that hasn't been produced yet, so...
Sometimes they depend on memory loads that take time, and sometimes they depend on control flow decisions. Consider this simple code fragment. If x neither 0, you're A also,
you're C plus D.
When the CPU reaches this branch instruction, it must evaluate the condition. But the result of XA0 may not be available yet. Maybe X was just loaded from memory. Maybe X depends on a previous instruction still executing. Until the condition is known, the CPU cannot know which instructions come next. Should it execute a plus B? Or plus D? If the processor simply waits for the answer, the pipeline stalls. And pipeline stalls are extremely expensive. Modern CPUs execute billions of instructions per second. Every cycle wasted waiting reduces performance dramatically. So CPU designers asked an important question. What if we didn't wait? What if we guessed? The core idea of speculative execution. Speculative execution means the CPU predicts what will happen next and executes instructions ahead of time. If the prediction turns out to be correct, the processor saves time. If the prediction turns out to be wrong, the CPU discards the speculative work and recovers. In other words, the processor moves forward as if the guess were correct.
This allows the pipeline to stay full.
It keeps execution units busy, and it dramatically increases overall throughput. Speculation is not limited to branches. Modern CPUs speculate on many things. Which branch will be taken,
Which instructions will execute next,
which memory loads are safe, whether dependencies exist, even whether certain instructions will fault. But branch speculation is where it all began. So let's start there. Branch prediction, guessing control flow. Branches create uncertainty in programs. They appear everywhere. Every loop contains a branch. Every conditional statement contains a branch. Programs often execute one branch every 5 or 6 instructions. If the CPU waited for every branch to resolve before continuing, performance would collapse. So processors use branch predictors. A branch predictor tries to guess whether a branch will be taken or not taken. For example, if Jordim right, is Jordim adrond comment to what you saw computed to diaries is only match no certity kubulkin, ocean hits is an 19 or so on tap thrice, null of tries if supportive voltage your detrifit 40 to 90. If this appears inside a loop, the branch will likely be taken many times before it eventually fails. A predictor can learn this pattern. Modern predictors store historical information about branches and use it to make predictions. When the CPU fetches instructions and encounters a branch, the predictor immediately provides a guess. If it predicts taken, the CPU begins fetching instructions from the target address. If it predicts not taken, it fetches the next sequential instruction. This decision happens extremely quickly, usually within a single cycle. But here's the important part. The CPU doesn't just fetch those instructions. It actually executes them, executing instructions before knowing the truth. That once the branch predictor makes a guess, the CPU behaves as if the guess is correct. Instructions from the predicted path enter the pipeline.
They move through
Decode the register renaming, scheduling. Substitute functional units begin performing real computations. Arithmetic operations happen. Loads access caches. Results are produced. All of this happens before the processor knows whether the branch prediction was correct. This is speculative execution. But the CPU must ensure something very important. Speculative instructions must not permanently change the architectural state until they are verified. Otherwise, wrong guesses would corrupt program execution. So processors separate two concepts: temporary speculative results, committed architectural state. This separation is handled by structures like the reorder buffer, which we discussed in a previous video. Speculation and the reorder buffer. In an out-of-order CPU, instructions execute in whatever order is most efficient. But they must retire in program order. The reorder buffer keeps track of all instructions currently in flight. When speculative instructions execute, their results are stored in temporary structures: physical register, load store buffers, reorder buffer entries. The architectural registers, the ones visible to the program, are not updated immediately. Instead, instructions wait in the reorder buffer. They remain speculative. Eventually, the branch instruction that started the speculation will execute. At that moment, the CPU finally knows the real outcome of the branch. If the prediction was correct, speculation becomes reality. Instructions can retire normally. Their results are committed. From the program's perspective, everything happened exactly as expected. But if the prediction was wrong, the processor must undo everything. When the CPU guesses wrong, branch predictors are good. Very good. Modern predictors often exceed 95% accuracy, but they are not perfect. Sometimes the processor guesses incorrectly. When that happens, the CPU detects a branch misprediction. At that moment, the processor must correct the pipeline.
A theorist that identifies the incorrect speculative instructions.
Every instruction younger than the mispredicted branch must be invalidated. These instructions are flushed from the pipeline. The reorder buffer discards them. Execution units cancel their work. Then the processor restarts instruction fetch at the correct address. This process is called a pipeline flush. We explored pipeline flushing in detail in an earlier video. The flushing wastes some cycles, but the performance trade-off is still overwhelmingly positive because most predictions are correct, which means speculation usually saves time rather than wasting it. Speculation beyond branches. Branches were the original motivation for speculation. But modern processors speculate in many other ways. Vika, enter you into our four. One example is memory speculation. Consider two instructions: store A, load B. If the CPU knows these addresses are different, it can execute the load immediately. But what if it isn't sure? The load might depend on the store. Waiting would stall the pipeline. So the CPU often speculates that the addresses are different and executes the load early. Later, if the store turns out to target the same address, the CPU detects the conflict and re-executes the load. Another form is dependency speculation. Sometimes the CPU predicts that instructions are independent, even when it isn't completely certain. If the guess is correct, execution continues quickly. If not, the processor recovers. Speculation appears throughout modern microarchitecture. It is deeply integrated with out-of-order execution, register renaming, load store queues, branch predictors. Branch predictors are instruction scheduling. Without speculation, these mechanisms would not reach their full potential. The performance impact of speculative execution allows CPUs to keep their pipelines busy. Remember that modern processors contain many execution units.
Integer alias.
Floating point units, IAD 2, crat up to 2 tupsern. Vector units, load store units. These units are extremely expensive pieces of hardware. They must be kept busy to justify their cost. Speculation ensures that instructions are always available to execute, even when the future of the program is uncertain. This dramatically increases instruction throughput. It also enables deeper pipelines. Without speculation, deep pipelines would stall, constantly waiting for control decisions. Speculation allows processors to run at extremely high clock frequencies while maintaining high utilization. In other words, speculative execution is a key reason modern CPUs are so fast. Speculation and the illusion of sequential execution. From the program's perspective, everything appears sequential. Instructions seem to execute one after another. Branches appear to resolve instantly. Results appear exactly when expected. But inside the processor, something very different is happening. Instructions are being executed early, out of order, speculatively, sometimes multiple times. The reorder buffer and retirement stage ensure that only the correct results become visible. This creates the illusion that the CPU is following the program exactly as written. But internally, the processor is constantly predicting, speculating, and correcting itself. It is effectively exploring possible futures of the program, the dark side of speculation. For decades, speculative execution was seen purely as a performance feature. But in 2018, researchers revealed something unexpected. Speculation could leak information. This led to vulnerabilities like Spectre and Meltdown. The key issue was that speculative instructions, even if eventually discarded, could still affect microarchitectural state. For example, cache contents might change, branch predictor state might change. These subtle changes could be measured by attackers. This allowed sensitive information to be inferred indirectly. The discovery forced the industry to rethink speculative execution. Hardware vendors introduced mitigations. Operating systems implemented defensive techniques. Speculation remains essential for performance, but it must now be managed carefully. Wise speculation is still necessary. Despite these challenges, speculative execution is not going away. Without it, CPUs would lose a massive amount of performance. Programs with frequent branches would slow dramatically. Pipelines would stall constantly. Execution units would sit idle. Speculation is one of the mechanisms that allows processors to approach their theoretical limits. It transforms uncertainty into opportunity. By guessing the future, CPUs avoid waiting. And when the guesses are right, which they usually are, the performance gains are enormous. The bigger picture, speculative execution is part of a broader philosophy in CPU design. Modern processors do not simply execute instructions. They predict, speculate, reorder, and optimize continuously. They look ahead. They prepare for multiple possible futures. They execute instructions before they are certain they are needed. And they maintain the illusion that everything happened in perfect order. Speculation turns uncertainty into parallelism. It converts control dependencies into opportunities for performance. And it allows processors to sustain the incredible speeds we expect from modern computers. Closing thoughts. So the next time your computer runs a program, remember this. Your CPU is not just executing instructions. It is predicting the future of the program. It is making educated guesses about branches, memory accesses, and dependencies. It is executing instructions that may never happen. And most of the time, those guesses are correct. Speculative execution is one of the reasons modern processors achieve such extraordinary performance. It is also a reminder that inside every CPU, beneath the clean abstraction of sequential code, lies an incredibly complex machine, one that is constantly thinking ahead. In the next video, we'll continue exploring the hidden mechanisms of modern processors. We'll look at how CPUs handle instruction rollback and recovery when speculation fails, and how the processor restores the correct architectural state after a misprediction. Because understanding recovery mechanisms reveals just how carefully modern CPUs manage the boundary between speculation and reality.